A piece of crystal found on a sunken ship holds an ancient secret. Centuries before magnetic compasses guided European sailors, Viking explorers crossed the North Atlantic under endless gray skies. They navigated a featureless ocean using the sun, stars, and a mysterious tool mentioned only in old sagas. This video will show you how a forgotten piece of technology, a so-called Sunstone, could have made these impossible voyages real. We will piece together clues from shipwrecks, physics labs, and thousand-year-old stories to solve one of history's greatest navigational puzzles. How did they find their way when the sun vanished for weeks? What does a simple crystal reveal about our ancestors' genius? By the end, you will see the past not as a dark age, but as a time of breathtaking innovation. What does it mean to truly master the world around you? The horizon was not a line but a promise, a vast and empty question mark drawn across the sea. For the Vikings, the ocean was not a barrier but a highway, and their ships were the keys that unlocked it. These were not the crude raiding vessels of popular legend, but sophisticated, flexible designs born from generations of living with the water. The classic longship, with its shallow draft and symmetrical ends, could sail up a river or across an open ocean with equal grace. It was a masterpiece of its time, a blend of oak and iron and human ambition. But a great ship is only part of the story. It needs a direction, and in the late 8th century, that ambition began to push beyond the sight of familiar shores. What began as seasonal raids on coastal monasteries evolved into something far more profound, a migration. Families packed their lives into hold spaces, seeking new land, new futures. They settled the remote volcanic shores of Iceland. They pushed further west, establishing farming communities on the icy edges of Greenland. And from there, the sagas tell us, a few determined souls made landfall on a continent they called Vinland, a place we know today as North America. Think about that journey for a moment, from the coast of Norway to the edge of Canada, crossing some of the most treacherous and fog-shrouded waters on the planet. This was not coastal hopping from headland to headland. This was true blue water sailing, where for weeks at a time, the only reference points were the sky above and the waves below. In such a void, how do you keep your course? How do you know you are sailing west and not drifting in a deadly circle? This was the monumental problem Viking navigators faced, a problem that made their voyages not just daring but almost unimaginable. And it is within this context of absolute necessity that we must search for their solution. The challenge itself created the perfect conditions for an ingenious, perhaps even beautiful, piece of technology to emerge. That uniform gray void had a name among sailors, a sky sea. It was the navigator's oldest and most formidable enemy. For days, sometimes weeks on end, the sun would simply vanish behind a seamless ceiling of cloud, and the stars at night were no more than a forgotten memory. In this world, every horizon line dissolved. The ocean became a featureless, heaving plain, and the ship, a tiny speck upon it, could be turning in circles without anyone on board ever realizing it. This was the daily reality of a North Atlantic crossing. We often think of Viking navigation in terms of clear skies and sharp stars, but their genius was forged in the fog. So what did they have to work with when their primary guides disappeared? Historians like Soren Thursland have meticulously studied the practical tools mentioned in sagas and records. They could watch the flight patterns of birds released from the ship, knowing certain species would fly toward the nearest land. They learned to read the subtle, long-distance swell of the ocean, a deeper rhythm beneath the wind-chopped waves. They observed the color of the water and the types of seaweed that floated by. These were brilliant methods of wayfinding, a kind of environmental literacy we have largely lost. But they all had one critical limitation. They could tell you if land was near or give you a very general sense of a persistent sea current, but they could not give you an exact, reliable heading. They could not tell you, with the precision required to cross 800 miles of open ocean, that you were sailing exactly west-southwest. For that, you needed a fixed reference point. You needed the sun. Its daily arc across the sky was the only true compass they had. From its rising and setting points they could find east and west. From its height at midday they could gauge how far north or south they had traveled. The sun was their anchor in the cosmos, but when it was swallowed by the sky sea, that anchor was gone. The ship was adrift in every sense. This then is the heart of the mystery. To reach Greenland, to even dream of a place like Vinland, they needed to maintain a straight course for unimaginable distances without their anchor. The environmental clues were not enough. The problem was absolute, and it demanded a solution that seemed to border on magic. It demanded a way to see the unseen. The answer may lie not in an artifact, but in a story. Centuries after the last Viking ship crossed the Atlantic, Icelandic scribes preserved a curious tale. In a 13th century saga known as Hrólfsdóttir, a king finds himself lost under a heavily overcast sky. Unsure of the sun's position, he is given a strange tool. The text describes a solarstein, a sunstone. Holding it up, the king is able to pinpoint the hidden sun's location and thus find his way. This brief, almost offhand mention is our strongest literary clue. But here we hit the first major fork in our investigation. Is this a record of a real, forgotten technology? Or is it simply a piece of poetic magic woven into a legendary narrative? The sagas are full of such elements: swords with names, prophetic dreams, and creatures of folklore. Scholars have long debated this very point. Some argue the sunstone was purely symbolic, a metaphor for wisdom or divine guidance in a Christianized text. Others note that its described use is strikingly practical, devoid of incantations or supernatural spectacle. It is presented not as a spell, but as a method. This distinction is crucial. If the sunstone was merely a myth, why does its described function solve the exact, real-world problem we just outlined? The saga doesn't mention it revealing buried treasure or speaking prophecies. It says it located the sun on a cloudy day. That is a specific answer to a specific, deadly navigational dilemma. This literary mystery forces us to look closer. Could a crystal truly perform such a feat? To move from the realm of saga to the realm of science, we must leave the parchment behind and step into a laboratory. The leap from saga to solid evidence began not on a ship, but at an old farm. In the 1940s, archaeologists working at a Norse settlement called Uunartoq in Greenland uncovered a curious wooden object. It was a half-circle of wood, roughly the size of a small plate, with a series of notches carved along its curved edge, and most intriguingly, a small hole drilled dead center. This fragment, known as the Uunartoq disk, became the first physical clue that Viking navigation involved more than just intuition. To researchers, the central hole suggested a gnomon, a small pin that would cast a shadow. The notches looked like intentional markings. Could this be the remains of a sun compass? The idea is elegant in its simplicity. On a clear day, at a known latitude, you could set the pin in the hole. As the sun moved, the shadow of the pin would sweep across the wooden surface. By marking where the shadow fell at specific times, perhaps aligning with those carved notches, a navigator could determine true north with remarkable accuracy. It was a fixed, reliable reference derived directly from the sun's path. Researchers like Gabba Horvath have built and tested replicas, proving the concept works. A navigator sailing from Norway to Greenland, for instance, would know the approximate latitude of their destination. Using this disk, they could calibrate their course daily, ensuring they were sailing the correct bearing west. This artifact demonstrates a sophisticated understanding of solar geometry. but it also presents us with that same inescapable limitation. It is a tool of light and shadow. On a cloudy day with no shadow to cast, the Uunartoq disk becomes a simple piece of decorated wood. It is a brilliant solution, but only for half the problem. It proves the Vikings had a method for clear weather. So what did they do when the clouds rolled in, as they always did on the North Atlantic? The existence of this artifact makes the question even more urgent. It shows they were thinking systematically about navigation. They were creating tools. The Sunstone, then, would not be a piece of magic, but the essential counterpart to this physical compass. It would be the part of the system that worked when the shadows disappeared. Physics provides the bridge between the Saga and the sea. To understand how a sunstone might have worked, we need to perform a simple experiment. On a bright, clear day, take a pair of polarized sunglasses, look up at the blue sky away from the direct glare of the sun, and slowly rotate the lenses. You will notice something remarkable. The sky itself appears to darken and lighten as you turn. You are not changing the light, you are filtering it, revealing a hidden pattern in the atmosphere that our eyes alone cannot see. This is the phenomenon of polarization. When sunlight scatters off the countless tiny molecules in our air, it does not just bounce randomly, it becomes organized, vibrating in specific directions. This creates a vast, invisible pattern across the entire dome of the sky, a kind of celestial watermark centered on the sun's position. Even when clouds obscure the sun itself, this polarized pattern remains imprinted on the light filtering through. Our eyes lack the ability to detect this directional quality of light, but certain crystals in nature do not. This is where a specific mineral becomes the key. A transparent crystal known as ICELAND SPAR, a form of calcite, possesses a unique property called birefringence. When a ray of light enters the crystal, it does not simply pass through. It splits into two separate rays, each traveling at a slightly different speed and taking a slightly different path. This creates a doubling effect if you look through it at text. More importantly for navigation, each of these two rays is polarized in a different direction. Imagine holding such a crystal up to a cloudy sky. You are not looking for an image of the sun. You are looking for a change in brightness. By rotating the crystal slowly, you would search for the orientation where the two images of the light coming through the cloud layer appear equally bright. At that precise angle, the crystal is aligned with the hidden polarization pattern in the sky, a pattern that radiates in concentric circles from the sun's location. Finding this point of equal brightness gives you a line pointing directly toward the sun, even if the sun itself is completely invisible. The crystal acts not as a magical lens, but as a sophisticated optical filter, translating an invisible atmospheric signature into a visible clue. It turns the entire sky into a subtle compass. This crystal has a name, ICELAND SPAR. It is not a rare jewel, but a clear, glassy form of calcite that fractures into perfect rhombohedral shapes like a skewed cube. It can be found in the volcanic rock of Iceland and across Scandinavia, lying in wait for anyone who knew what to look for. Its beauty is in its clarity and its profound physical secret. Long before it was proposed as a Viking sunstone, this very crystal was causing a revolution in human understanding. In the 1660s, a Danish scientist named Erasmus Bartholin was handed a piece of ICELAND SPAR by a sailor. When he placed it over a piece of paper with a single dot, he saw not one dot but two. He had discovered the phenomenon of double refraction, the first concrete evidence that light could behave in ways that defied common sense. This crystal became a cornerstone of optics, helping scientists like Christian Huygens and later Augustin Jean Fresnel unravel the waved nature of light. So this object sits at a fascinating crossroads. To a 17th-century physicist, it was a laboratory marvel that revealed the fundamental properties of the universe. To a Viking navigator centuries earlier, that same double image could have been the difference between life and a slow, disorienting end lost at sea. The principle is elegantly practical. As physicist Ropars and his team have demonstrated, you do not need to see the sun to use the spar. On a completely overcast day, you simply hold the crystal up and look through it toward the patch of sky where you suspect the sun to be. You will see two faint, overlapping images of that patch of light. Then you slowly rotate the crystal. Your goal is not to find the sun's disk, but to find the point where those two images become identical in brightness. When they merge into a single, uniform glow, you have found it. The crystal's axis now points directly along the polarization pattern, leading straight to the sun's hidden position. You have just taken a bearing from an empty gray sky. Modern experiments have proven this works with remarkable accuracy, often within a single degree. Think of it as tuning a radio. You are turning a dial, the crystal, through static, the diffuse cloud light, until you hit the clear signal, the precise alignment with the sun's polarized signature. It is a silent, patient process of alignment, not revelation. This transforms the Sunstone from a mythical artifact into a plausible, even likely, piece of technology. It was a naturally occurring tool, readily available in their homeland, that performed one specific, vital function with elegant efficiency. It bridged the clear weather utility of the wooden sun compass with the brutal reality of the North Atlantic sky. The Saga's brief mention now reads less like fantasy and more like a technical manual, a single sentence preserving a method that physics confirms is not only possible but profoundly clever. But a theory, no matter how elegant, needs proof. The idea of the Sunstone was a beautiful story supported by physics, yet it remained a shadow on the wall of history. To move it into the light required something definitive, a controlled experiment that could silence the skeptics. That moment arrived in a laboratory in Rennes, France, in 2011. A team led by researchers Ropars and Albert Lefloc set out to do what no Saga could. They aimed to recreate the exact conditions a Viking navigator would have faced and put the crystal to a scientific test. Their setup was both simple and brilliant. They constructed an artificial sky, a dome that could be lit to mimic the specific polarized patterns of our atmosphere. Instead of the real sun, they used a precise light source, carefully calibrated to act as their hidden celestial marker. Then they took a key artifact, a perfectly clear, rhomboid-shaped piece of ICELAND spar, believed to be from the Viking era and found in an English shipwreck. This was not a modern replica, but a crystal that had existed for centuries, waiting for its purpose to be understood again. The methodology was meticulous. Under this artificial, cloudy sky, a participant would use only the crystal, rotating it slowly just as a navigator would have, searching for that critical point where the double images merged into equal brightness. They repeated this process hundreds of times from different simulated positions, under varying intensities of light, meant to represent everything from thin haze to dense, sunless overcast. The results were nothing short of a eureka moment. The crystal allowed them to pinpoint the hidden light source's position with an accuracy of just a few degrees. Even under the thickest simulated cloud, the method worked. Ropars described the finding with clear excitement, noting that the precision was more than sufficient for navigation across the open sea. This was the validation the hypothesis needed. The laboratory proof transformed the Sunstone from a speculative footnote in a saga into a credible, even likely, piece of historical technology. It demonstrated that the tool did not require magical properties, only a deep, observational understanding of light itself. The Vikings did not need to understand the wave theory of polarization. They only needed to recognize a consistent, repeatable effect in the sky above them and possess the natural tool to decode it. This experiment marked a major breakthrough, shifting the question from if such a method was possible to how seamlessly it could have been integrated into the daily practice of finding a way home. The laboratory proved the principle, but the North Atlantic was the ultimate test. Imagine the scene not from a clean room, but from the deck of a longship. A figure stands near the prow, a person known in the sagas as a Leith Sugumada, a pathfinder. The sky is a uniform, oppressive grey, the wind is a constant presence, and the ship rises and falls on a deep, rolling swell. In their hand is not a complex instrument, but a simple, translucent crystal. This is where theory meets the salt spray of practice. How would this actually work on a voyage from Iceland to Greenland? Let us walk through the likely steps, a dance between human intuition and optical physics. The process would begin not in the fog, but in a moment of clarity. At dawn on a rare clear day, the navigator would first use the crystal to confirm what they could already see. Holding the ICELAND SPAR up, they would locate the true sun, watching the double images merge as they rotated the stone. This simple act served as a vital calibration. It confirmed the crystal was working and reinforced in the navigator's mind the exact feel of that alignment, the look of that equal brightness against the known backdrop of the sun. It built a sensory memory, a reference point for the days when no reference would be visible. Now the clouds close in. The world shrinks to the circle of waves around the ship. This is when the crystal becomes indispensable. The navigator would face the general direction where the sun should be, based on the time of day and their mental map of its passage. Holding the crystal steady, they would slowly rotate it, peering through the clear mineral at the featureless gray above. Their eyes are not searching for shape, but for subtle contrast. They watch the two faint, overlapping images of the cloud light, waiting for that moment of equilibrium, that point where the two glowing patches become one uniform shade. When they lock into that position, they have a line. The axis of the crystal now points directly toward the hidden sun. They might then call out a bearing to the helmsman or mark a temporary line on the ship's rail. They have just arrived a fixed celestial bearing from an empty sky, but a single bearing is a snapshot. To set a course, you need a relationship to north. This is where the navigator's toolkit reveals its clever integration. If the clouds broke for even a few minutes, revealing a faint, diffuse glow where the sun was located, they could spring into action. Using that now visible light source, they could quickly employ their shadow casting tool, like the Uunartoq disk. By aligning the disk so its central pin cast the faintest of shadows onto the correct notch, they could establish true north with precision. The Sunstone gave them the sun's location in the fog, and the shadow compass allowed them to translate that location into a lasting directional reference the moment conditions permitted. It was a 1-2 punch of ancient ingenuity. This was not a simple matter of reading a gauge. It was an art honed by experience. The navigator had to account for the ship's movement, the changing angle of the light through the day, and the feel of the crystal in their hand. They needed to understand the rhythm of the sky itself, interpreting the quality of the gray light. Was it the thin, high overcast that still carried a strong polarized signature, or the thick, woolen fog that muted the signal? This knowledge was not written in a manual. It was carried in the bones and the memory of countless voyages. It was a science of observation elevated to an intuitive craft, a dialogue between a human mind and the hidden patterns of the world. The true genius of the Sunstone lies not in the crystal itself, but in the mind that learned to ask the sky a question it never thought to answer. The Viking Sunstone was not an isolated miracle, but one brilliant answer to a question the whole world was asking. Across the globe, in different seas under different skies, human cultures were performing their own navigational miracles, each sculpted by the environment they had to master. To truly appreciate the Viking achievement, we must see it within this wider tapestry of wayfinding. Consider the vast Pacific Ocean, a realm of scattered islands separated by thousands of miles of open water. Here, Polynesian navigators developed a system so refined it feels like a sixth sense. Without written charts or magnetic compasses, they learned to read the ocean itself. They memorized the subtle directional patterns of swells, feeling the long, deep rhythms of the sea through the hull of their canoe. They observed the flight paths of specific birds at dawn and dusk, knowing their range indicated the proximity of land unseen over the horizon. They navigated by a mental star compass, a celestial map where the rising and setting points of hundreds of stars served as fixed bearings. Their knowledge was an oral encyclopedia of the natural world, passed down through generations. It was a method built on profound observation and memory, a living dialogue with wind, wave, and star. On the other side of the world, Arab traders navigating the Indian Ocean and beyond used a different tool for a different challenge, measuring latitude. Their instrument was the camel, a simple wooden rectangle with a knotted string. By holding the board at arm's length and aligning its top and bottom with the horizon and a specific star, like the North Star, the navigator could measure the star's altitude. By comparing this measurement to known values recorded on the string's knots for different ports, they could determine how far north or south they had sailed. It was a brilliant, portable solution for east-west travel along known latitudes. Now, place the Viking method beside these. The Polynesian system was holistic, weaving together a symphony of environmental clues. The Arab camel was a precise geometric tool for stellar measurement. The Viking sunstone, by contrast, was a mineralogical key to a single, persistent problem, the absent sun. Anthropological studies highlight this fascinating divergence. Each culture solved the universal problem of open ocean travel by leveraging the specific clues their environment offered most reliably. In the consistently clear nights of the Pacific and the Arabian Sea, the stars were a dependable compass. In the perpetually clouded North Atlantic, they were not. The Vikings lived in a world of low star visibility and frequent overcast, a world where the sun, even when hidden, was the only constant celestial reference. Their innovation was to find a way to pull a directional signal from the very fabric of the cloudy daylight sky, using a crystal nature provided. This comparative view does not rank one method above another. Instead, it reveals a profound truth about human ingenuity. Faced with the same existential need to traverse the unknown, our ancestors looked at their unique worlds and asked different questions. The Polynesians asked the ocean for its secrets, the Arabs asked the stars for their angle, the Vikings asked the cloudy sky for a hidden line of light. Each culture developed a beautiful, effective adaptation, a testament to the diversity of human intelligence. The Sunstone, therefore, stands not as a mysterious anomaly, but as a specific and brilliant adaptation to a specific and brutal environment. It reminds us that innovation is not just about invention, but about keen observation, about learning to see the invisible patterns in the world immediately around you. But a story carved in wood and proven in a lab still lacks one final piece, an artifact. For decades, the Sunstone remained a ghost in the historical record, a brilliant idea without a physical specimen to hold. That changed with the silty waters of the English Channel. In 2002, marine archaeologists investigating the wreck of an English warship named the Alderney made a curious discovery. The ship, lost in the late 16th century near the Channel Islands, was a time capsule of Elizabethan seafaring. Among its scattered remains, near classic navigational instruments like dividers and sounding leads, lay a small, opaque object. Recovered and cleaned, it revealed itself not as a stone or a piece of glass, but as a smooth, rounded piece of calcite crystal ICELAND SPAR. This was the Alderney crystal. Its physical description is telling. It was not a raw, jagged mineral specimen. It had been worked, shaped into a roughly rectangular form with rounded edges, smoothed lightly by hand and by the sea. Its size, about that of a small bar of soap, fit comfortably in a palm. Most importantly, its context was everything. It was found not with personal effects or cargo, but in direct association with the tools of the ship's master, the individual responsible for plotting the vessel's course. The excavation team, led by marine archaeologist Menson Bound, was immediately struck by the implications. In their reports, they posed the question directly. Could this be a sunstone, a genuine historical example of the very tool described in the sagas and tested in the labs? The discovery ignited a fierce and fascinating debate among historians. The central issue is one of chronology. The Alderney sank in the 1590s, centuries after the end of the Viking Age. By this time, the magnetic compass was a standard, well-understood instrument on European ships. So why would a 16th-century English navigator need a piece of ICELAND spar? One school of thought argues it was indeed a functional tool, a sunstone. They point out that magnetic compasses of the era were notoriously unreliable, especially on ships built with increasing amounts of iron, which could distort the needle. A crystal that could find the sun on a cloudy day would provide a priceless, independent check on the compass, a way to verify true north when the magnetic needle swung erratically. In this view, the knowledge of such crystals may never have fully disappeared. It could have persisted as a piece of folk technology among northern sailors, a secret trick of the trade passed from master to apprentice, only to be formally rediscovered by science centuries later. The other perspective is more cautious. Skeptics suggest the crystal could have had a dozen other uses. It might have been a magnifying lens for lighting tinder, a decorative object, or simply a curiosity picked up on a voyage to Iceland, a sailor's souvenir with no practical function at all. The debate hinges on that single, powerful word, context. Finding a crystal in a field means nothing. Finding this specific crystal, smoothed by handling, nestled among the very instruments used to guide a ship through treacherous waters, speaks a different, more compelling language. As the excavation report notes, the association is too deliberate to be easily dismissed as coincidence. Whether a direct descendant of Viking technology or a parallel rediscovery, the Alderney crystal serves as a tangible, thrilling link. It drags the Sunstone out of the realm of pure theory and places it firmly into the gritty, real world of seafaring. It suggests that the idea of using a crystal to navigate did not die with the last longship. It whispers that this elegant solution to an ancient problem may have lingered in the collective memory of those who challenged the grey Atlantic, a secret written not in sagas, but in the very light of the sky. The crystal was not a Viking GPS. This dramatic but misleading idea risks turning a profound human achievement into a piece of fantasy technology. To truly appreciate what the Sunstone was, we must also understand, in clear and specific terms, what it was not. It did not provide a blinking dot on a map. Its capabilities, while ingenious, were tightly bound by the laws of physics and the realities of the North Atlantic environment. First and foremost, the Sunstone could not tell a navigator their latitude, their north-south position on the globe. Determining latitude requires measuring the angle of the sun above the horizon at its highest daily point, a task for tools like the Arab camel or the Viking's own shadow board. The Sunstone gave only a bearing, a line pointing toward the hidden sun. It could tell you the sun was that way, but not how high in the sky it was. This meant it could not, on its own, tell you if you had drifted too far north toward the pack ice or too far south off your intended track. It was a compass needle, not a coordinate. Second, its ability to pinpoint the exact time of day was limited. While a skilled navigator might roughly gauge the sun's progress across the sky by taking repeated bearings, the crystal did not offer the precise, minute-by-minute timekeeping needed for advanced celestial navigation. It was not a clock. Third, and crucially, the Sunstone had its own blind spots. It was utterly useless at night when the sun's polarized signature was absent. And under certain conditions, like a uniformly thick, dark storm cloud or dense, driving rain, The polarization pattern in the sky could become too scrambled or faint for the crystal to detect a clear signal. It was a tool for gray overcast and haze, not for the black heart of a tempest. Recognizing these limits is not a dismissal of the technology. On the contrary, it is what makes the Viking navigators' skill so breathtakingly human. They did not have a magic box that solved every problem. They had a specialized tool for one specific critical task, maintaining a heading when their primary celestial reference vanished. This tool was then woven into a larger, living system of knowledge. The Sunstone gave them a bearing. Their understanding of ocean currents, bird behavior, and wave patterns gave them context. Their memory of star paths and the rare clear sightings with their shadow compass gave them calibration. It was this synthesis, the crystal's precise line combined with the navigator's environmental wisdom, that formed the complete system. By tempering the narrative with these physical realities, we actually strengthen the historical case. A magical, all-powerful sunstone belongs in a saga. A clever, limited, but highly effective optical tool belongs on the deck of a longship. The truth is more impressive than the myth because it reveals not a superweapon, but a profound intimacy with the natural world. They learned to ask the sky a subtle question, and the sky, through a simple crystal, answered. The crystal was inert, a silent piece of the earth. Its power came alive only in the hands of someone who knew its language. This truth shifts our focus from the tool itself to the mind that wielded it, from the hardware to the indispensable human software. In a world without manuals or written coordinates, the most vital navigational technology was not carved from crystal or wood, but woven from memory and spoken word. It lived in the oral tradition, passed like a sacred flame from an experienced pathfinder to a watchful apprentice during the long winter nights or on the deck under the stars. This was knowledge earned through direct, perilous experience, then distilled into stories, rhymes, and rigorous practice. The master would not just show how to hold the sunstone, but would describe the specific feel of the light on a day when the high clouds made the crystal sing with clarity, versus the stubborn dimness of a woolen sea fog. They would teach the rhythm of the observation, how to account for the ship's roll, how to trust the reading even when every instinct screamed that the sky was empty. This mentorship transferred more than technique. It transferred a way of seeing the world. The sunstone gave a precise bearing, but that single data point was meaningless without a vast library of contextual knowledge to give it purpose. The navigator's mind held charts written in the behavior of other species. They knew the seasonal migrations of certain seabirds, like the fulmar or the puffin, whose flight paths at dusk could point toward the nearest landfall, sometimes dozens of miles beyond the horizon. They recognized the deep, regular swell from a distant storm, a submerged highway that could hold a steady direction for days, a constant reference beneath the shifting wind-chopped waves. They learned to read the color of the water, the pale green of coastal shallows, the deep indigo of the open ocean basin, the silt-brown runoff from a distant river mouth. They noted where whales preferred to feed. Understanding these giants followed underwater contours that often led toward certain shores. Each of these clues was a piece of a grand, living puzzle. The sunstone's bearing told you which way was west, but the flight of a lone bird might tell you that west was now slightly south of your heading to avoid a treacherous current. The change in the swell's feel through the hull might confirm you had entered the great north-flowing stream that would sweep you toward Greenland. This was not navigation by gadget, but navigation by conversation, a continuous dialogue between the navigator and a dozen whispering elements of the natural world. The crystal provided the clearest voice in that dialogue, but it was never the only one speaking. This leads us to a haunting reflection. We can recover a sunstone from a shipwreck and test its physics in a lab. We can theorize about the use of a shadow compass. But how much of that nuanced, experiential wisdom is simply gone? The specific rhyme that encoded the whale's path in a certain month, the exact description of the wave pattern that meant Iceland was near, the subtle difference in the sky's gray tone that signaled a clearing front, these lived in the minds of individuals, transmitted through generations by word of mouth and shared experience. When that chain was broken, when settlements faded or cultures transformed, that vast library of subtle environmental literacy vanished into silence. It highlights a profound truth about this entire endeavor. The Vikings did not conquer the Atlantic because they had a clever crystal. They succeeded because they cultivated a specific type of genius, the trained, observant, and deeply intuitive human mind. The tool and the mind existed in a perfect synergy. The Sunstone offered a thread of certainty through the gray void, and the navigators accumulated wisdom wove that thread into a rope strong enough to pull a ship across an ocean. One was useless without the other. This partnership between human understanding and natural tool is perhaps their greatest legacy, a reminder that the most advanced technology in any age is, and always has been, a mind taught to see what others overlook. This partnership between mind and crystal unfolded within a specific window of time, a climatic chapter that favored bold voyages. To understand why the Viking age of exploration happened when it did, we must look beyond the ships and into the very ice of the North Atlantic itself. Paleoclimatologists, scientists who study ancient climates, have pieced together a fascinating portrait of this era using natural archives. They drilled deep into Greenland's ice sheets, extracting long cores that act like frozen time capsules. Each layer of snow, compacted over centuries, holds tiny bubbles of ancient atmosphere and chemical signatures that reveal past temperatures. They study sediment layers on the ocean floor, analyzing the shells of tiny creatures that thrived in specific water conditions. Together, this evidence sketches a period from roughly the 9th to the 13th centuries known as the medieval warm period. It was not a global heatwave by modern standards, but a regional climatic anomaly that made the North Atlantic marginally, yet meaningfully, more forgiving. Average temperatures in the region were slightly higher than in the centuries immediately before or after. This subtle shift had profound practical consequences. The extent of Arctic sea ice likely retreated further north during the summer months, opening navigable corridors that were previously choked with bergs and pack ice. The storm tracks, those tempestuous highways of low pressure that sweep across the ocean, may have shifted slightly or become less intense for a time. This created a window of somewhat more predictable sailing conditions. Think of it not as a calm sea, but as a notoriously rough sea that became slightly less ferocious for a few generations. The voyages were still monumental feats of endurance and skill, but the odds of surviving a crossing from Iceland to Greenland improved when the ice fields were smaller and the gales perhaps less frequent. This climatic context is a crucial piece of the puzzle. It does not diminish the Vikings' achievements, but rather frames them with greater clarity. The navigational technology, the Sunstone, the shadow board, the environmental wisdom was the key that unlocked the ocean. But the medieval warm period provided an unlocked door. It was the environmental stage upon which their drama of exploration could be performed with a slightly higher chance of success. It made the repeated, sustained voyages necessary for colonization not just possible but plausible. This interplay between human ingenuity and environmental opportunity is a recurring theme in history. The Vikings did not control the climate, but they possessed the tools and the courage to recognize and exploit a favorable shift when it arrived. Their story becomes not one of conquering an immutable, hostile nature, but of navigating a complex and changing relationship with the world itself, using every resource, mineral, mental, and meteorological at their disposal. The ultimate proving ground for this technology was not the crossing to Greenland, but the leap into the absolute unknown. From the remote western settlement of Greenland, The next logical horizon was not another island, but a continent. The sagas tell us this journey was made by Leif Erikson, son of Erik the Red, around the year 1000. His destination was a place he called Vinland, a land of mild climate, wild grapes, and vast forests. To get there, he and his crew had to cross the Labrador Sea, a stretch of water that represents the purest form of the navigator's nightmare. This was not a voyage along a latitude line with a known destination. It was a purposeful strike southwest into a void, a journey that demanded not just survival, but precise landfall on a coast no Norse sailor had ever seen. The Saga of the Greenlanders describes the route with a navigator's eye. They sailed from Greenland out into the open ocean, then turned southwest. They first encountered a barren, glacier-covered land they called Helluland, likely modern-day Baffin Island. Continuing south, they found a wooded coast with white sandy beaches, Markland, which we believe is Labrador. Finally, pushing further, they made their winter camp at a place with such abundant resources they named it Vinland. This was not a story of accidental drift. It was a deliberate, multi-stage expedition. The most critical leg was the initial open water crossing from Greenland's tip to the Canadian Arctic archipelago. This meant sailing for days, perhaps a week or more, across nearly 400 miles of the Labrador Sea, an area infamous for dense fog, drifting icebergs, and sudden, brutal storms. Here, the coastline was not a guide but a trap, lined with uncharted rocks and ice. The safe approach was to stay well offshore in the featureless gray expanse until they could swing south toward their target. This is where the Sunstone moves from a helpful tool to an indispensable one. Let us consider the celestial data available to them. Leif's voyage likely occurred in late summer or early autumn, a time chosen for calmer seas after the spring ice melt. In these northern latitudes, the sun's path is lower in the sky, and the period of daylight, while still long, is shrinking. Crucially, the sun would have been moving almost directly along an east-west line from their perspective. To sail southwest, they needed to hold a bearing roughly midway between where the sun rose and where it set. On a clear day, a shadow compass could establish this. But the historical climate data and modern experience tell us clear days were the exception, not the rule, on that crossing. For sustained periods, their world would have been the sky-sea. The Sunstone hypothesis finds its most compelling application right here. To maintain that crucial southwesterly heading day after gray day, they needed a fixed reference. The ocean swell might give a general sense, but it could be twisted by local winds. Birds were useless in mid-crossing. Only the sun, even hidden, provided a true anchor. By using the crystal to take a bearing on the obscured sun twice daily, once in the morning and once in the afternoon, a skilled pathfinder could plot its invisible arc across the sky. From that arc, they could deduce the east-west line and thus hold their course relative to it. It provided the consistent directional confidence to turn a potentially suicidal gamble into a calculated risk. They were not sailing blind into the fog. They were following a hidden thread of polarized light stretched across the ocean. This transforms the saga from a mere adventure tale into a plausible record of technical achievement. The journey to Vinland was not a mythic accident, but the pinnacle of a navigational system that had been refined over generations. It was the system that allowed them to leave sight of Greenland with the confidence that they could find something, and then, miraculously, find their way back home to tell the tale. The Sunstone was the key component that made such confidence possible in a world of cloud and sea. Yet the very tool that enabled these journeys would itself be lost to the waves of time. If the Sunstone was such a brilliant and effective key to the North Atlantic, why did its use fade into obscurity, remembered only as a cryptic line in an old saga? The answer lies not in a single event, but in a confluence of historical shifts that slowly rendered this specific genius obsolete. Our story now turns from open ocean to a shrinking world, beginning with the slow, quiet end of the Norse settlements in Greenland. For centuries, these outposts had been the vital way stations, the living proof that the navigation system worked. But by the 15th century, the last written records from Greenland ceased. Archaeological evidence suggests a combination of factors led to their decline. A cooling climate, what scientists call the Little Ice Age, made farming more difficult and increased the sea ice, blocking crucial trade routes. Contact with Iceland and Norway became sporadic, then ceased altogether. The specialized knowledge of the pathfinder, the guild secrets of reading sun and crystal, depended on a living chain of teachers and apprentices on ships making regular voyages. When the ships stopped sailing, the chain was broken. The knowledge, no longer practiced or passed down, began to evaporate from living memory. It became a story told by the fire, not a skill taught on the deck. At nearly the same time, a new technology was spreading north from the Mediterranean world, one that would revolutionize navigation for everyone. The magnetic compass arrived in Europe around the 12th century. Its principle was beautifully simple. A magnetized needle floating on water or pivoted on a pin would consistently point toward the magnetic North Pole. It worked night or day, in fog or under clear skies. It required no understanding of polarization, no patient rotation toward equal brightness. You simply looked at the needle. For most sailors on most routes, this was a game changer. It democratized direction finding. While the Sunstone required years of nuanced training to interpret subtle optical clues, a compass could be used by a relative novice after a brief explanation. The compass was not necessarily more accurate for determining true north. It pointed to magnetic north, which varies from true geographic north and shifts over time, but for maintaining a consistent heading, it was incredibly reliable and, crucially, far easier to use under a wider range of conditions. The arrival of this simpler, more versatile tool likely made the complex, specialized art of the Sunstone seem like an unnecessary relic. Why train for years in a dying oral tradition when a new device could give a good answer in an instant? This highlights a profound and often overlooked truth about technology. It is not always the best or most sophisticated tool that survives, but the one that best fits the changing ecosystem of its users. The Sunstone was a masterpiece of adaptation to a specific, brutal environment, the cloudy North Atlantic of the Viking Age. But as that world changed, as trade routes shifted, settlements faded, and simpler instruments became available, the very conditions that demanded the Sunstone's unique capabilities began to disappear. The knowledge was likely guarded, a secret of a specialized navigators' guild, which protected its power but also made it more vulnerable. When the last master of the craft in Greenland passed without an apprentice, that branch of the tradition died forever. It was not overthrown in a battle or banned by decree. It simply withered from disuse, a brilliant solution in search of a problem that no longer existed in the same form. This is the quiet tragedy of so much human innovation. Practical arts are not lost in cataclysms, but in the slow turning of generations, in the shift of economic currents, in the replacement of a complex, deeply understood skill with a simpler, more convenient black box. We are left to wonder what other elegant solutions to ancient problems have vanished just as completely, leaving behind only a faint echo in a story or a strange object in a shipwreck whose true purpose we must painfully reconstruct. The theory needed the open ocean to breathe. For all the laboratory precision and historical analysis, one question remained unanswered. Could a person standing on the deck of a rolling longship actually use this method to cross an ocean? In 2018, a bold modern experiment set out to find out. A crew of sailors and researchers embarked on an Atlantic crossing aboard the Harald Harfager, a meticulously built replica of a Gokstad ship, using a calibrated ICELAND SPAR crystal as their primary navigational tool. Their mission was not to prove the Vikings had GPS, but to experience firsthand the practical realities and limitations of this ancient technique. The crystal was their guide, but a discrete GPS unit, hidden from the Navigator, served as the silent judge, logging their true position for later comparison. This was not a simulation. It was a journey into the living classroom of the North Atlantic, with all its fog, swells, and sudden squalls. Sailors reported the profound mental shift required. You are not simply reading an instrument, you are learning to converse with the sky. On days of high, thin overcast, the crystal performed beautifully. The Navigator, after careful rotation, would call out a bearing. The helmsman would adjust course, and hours later, the GPS data would confirm they had held a remarkably straight line, often within a few degrees of their intended heading. The method worked. It provided a consistent, reliable reference point from an apparently featureless gray dome. But the voyage also revealed the authentic challenges, the human factors no lab test could capture. Eye strain became a real issue. Staring through the crystal at the diffuse brightness of the sky, searching for that moment of equal illumination, demanded intense concentration and could lead to fatigue. It required practice, a building of what one sailor called a muscle memory for light. The technique faltered under the densest, darkest storm clouds, where the polarized signal was too scrambled to detect, confirming the historical limits of the tool. Perhaps the most telling insight was the need for patience. This was not a quick glance. A single reliable bearing could take several minutes of careful observation and adjustment, a meditation in the midst of a storm-tossed deck. The modern crew gained a deep, visceral respect for the Viking pathfinder. This was not a passive technology, but an active skill. The crystal did not give you a course, it gave you a clue that your mind and experience had to interpret. The success of the Harald Hårfagre voyage provided something beyond data. It offered experiential proof. It demonstrated that the system was not just physically possible, but practically viable in the exact environment for which it was designed. The crew lived the answer, feeling the weight of the crystal in their hand, and the triumph of a verified bearing emerged from the gloom. They connected across 1,000 years with the quiet focus of a figure on the prow, turning a piece of the earth toward the hidden sun and finding a way forward. The voyage of the Harald Hårfagre provided a human-scale test, but what about 1,000 voyages? To move from a single journey to a statistical certainty, researchers have turned from the heaving deck to the silent hum of a supercomputer. Here, in the realm of ones and zeros, a new form of digital archaeology is being conducted. Scientists build intricate software models that simulate the North Atlantic not for days, but for centuries of virtual time. They create a population of digital Viking ships, each commanded by an AI navigator with a set of programmed skills and tools. The goal is not to replay history, but to explore its probabilities. What were the odds of reaching Greenland with a Sunstone versus without one? The models begin by building a world. They feed in paleoclimate data to recreate the likely weather patterns, cloud cover, and storm frequencies of the medieval warm period. They map the ocean currents and the known sea ice extent. Then they define their virtual voyages. Parameters are set for navigation error, how far off course a sailor might drift per day using only waves and birds, compared to the tighter margin of error allowed by a tool that could take a solar bearing through overcast. They assign probabilities for catastrophic events, like being driven far off course by a multi-day storm. With the stage set, they hit run. The computer executes not one, but 10,000 simulated crossings from Norway to Greenland. In one batch, the digital navigators have only traditional wayfinding methods. In another, they are equipped with a simulated Sunstone, an algorithm that allows them to correct their heading based on the hidden sun's position whenever the cloud cover in the model permits its use. The results are not stories but statistics. Across countless digital runs, a clear pattern emerges. The success rate defined as making landfall within a viable stretch of the Greenland coast. shows a significant and consistent increase when the Sunstone is part of the toolkit. The models quantify what the sagas imply. They show that while a skilled navigator could sometimes succeed without the crystal, their chances of a fatal miss or a disastrous drift into the ice-packed north were far higher. The crystal acted as a statistical lifeline, narrowing the cone of navigational uncertainty just enough to tip the odds from a desperate gamble into a calculated endeavor. This digital evidence is powerful because it is blind to legend. It does not care about heroic tales or cultural bias. It simply processes variables and calculates outcomes. When the output consistently shows that adding this one tool dramatically improves simulated survival rates, it offers a compelling, numbers-based argument for its historical use. It complements the physical crystal from the Alderney wreck and the laboratory proof from Rennes, forming a third, robust pillar of evidence. We are left with a profound convergence. The literary hint, the optical principle, the artifact from the sea, the modern voyage, and now the algorithmic verdict, all point in the same direction. They sketch the silhouette of a lost technology, not with a single bold stroke, but with a mosaic of evidence, each piece reinforcing the other. The digital world, in its cold logic, warmly affirms the ingenuity of the ancient mind. But every compelling theory must face its critics, and the Sunstone hypothesis is no exception. Within academic circles, a healthy and rigorous debate continues, a reminder that history is often a conversation, not a verdict. Many respected historians and archaeologists urge profound caution, pointing to significant gaps in the evidence that prevent us from declaring the case closed. Their skepticism is not dismissal, but a commitment to the discipline's highest standards. The most prominent objection is an archaeological one. Despite the tantalizing find of the Alderney crystal on a much later ship, no definitive sunstone has ever been recovered from a confirmed Viking Age maritime site. Not a single piece of worked ICELAND spar has been found in the grave of a navigator, lashed to the wreck of a longship, or stored among the tools of a Greenlandic farmstead from that era. This absence of a smoking gun, critics argue, is deafening. If this tool was so central to their oceanic expansion, why is there no direct physical proof from the time and culture in question? Some scholars propose alternative interpretations of the Saga references. When the old texts speak of a solarstein, could they be describing a different kind of mineral altogether? Perhaps it was a simple piece of translucent horn or talc used as a primitive lens to focus the sun's rays for fire starting, or even a component of a more conventional sundial. The word itself, they note, is ambiguous. Furthermore, a compelling school of thought suggests that Viking navigators were simply so exceptionally skilled at dead reckoning, the art of estimating position based on speed, time, and direction, that they had no need for such a specialized optical device. They argue that generations of accumulated experience reading waves, winds, wildlife, and the rare celestial sighting provided all the information necessary for successful crossings. The voyages, in this view, were triumphs of human intuition and environmental literacy, not of crystal-assisted technology. As historian Anton Englert has noted, the leap from a plausible physics experiment to a proven historical practice is a wide one. He and others emphasize that while the Sunstone is a beautiful and clever solution, we must distinguish between what was possible and what was actually done. The historical record, they maintain, remains stubbornly silent on the specifics of its use. This skepticism serves a vital purpose. It prevents a fascinating hypothesis from hardening into uncritical dogma. It forces proponents to refine their arguments, to search for new evidence, and to acknowledge the limits of what we can truly know. This tension between possibility and proof is the very engine of historical discovery. It reminds us that the past often guards its secrets closely, revealing them in fragments and whispers, not in complete instruction manuals. The Sunstone debate, therefore, is not a weakness in the story, but a sign of its intellectual vitality. It showcases history as a living science where ideas are tested, challenged, and continually reshaped by evidence. This honest engagement with uncertainty, far from undermining the narrative, ultimately makes it more trustworthy and rich. We are left not with a neat, packaged answer, but with a genuine mystery, one that honors both the ingenuity of the Vikings and the rigorous curiosity of those who seek to understand them. The debate in academic journals was just the beginning of the Sunstone's voyage. Its real journey into the modern world started when it leapt from the pages of research into the realm of story. A tool of subtle science and patient observation was destined for a transformation, reshaped by our collective hunger for wonder. This crystal first captured wide public attention through dramatic portrayals in historical dramas like the television series Vikings. There, it is often shown as a mystical, glowing object, held aloft by a seer or a king in a moment of climatic decision, cutting through fog and doubt with cinematic certainty. This visual shorthand is powerful. It communicates the concept instantly to an audience. Here is a magical compass from the past. Yet this amplification comes with a trade-off. The slow, meticulous practice of aligning the crystal, the squinting at faint double images against a gray sky, is replaced by a moment of visual spectacle. The tool becomes less a piece of clever physics and more a relic of pure mysticism, a prop that signifies ancient wisdom without explaining its mundane, brilliant mechanics. This romanticization serves a purpose. It makes a complex historical idea accessible and thrilling, planting the seed of the Sunstone in millions of minds. But it also risks creating a new kind of myth, one where the line between Viking technology and Viking magic becomes beautifully, permanently blurred. This cultural repackaging extends far beyond television. The Sunstone has been eagerly adopted by fantasy literature and video games, where it is frequently upgraded from a navigational aid to a full-fledged magical artifact. In these worlds, it might open hidden doors, reveal enchanted maps, or channel elemental powers. Its name and its Norse origins provide a perfect veneer of historical plausibility for fantastical plots, lending an air of gritty authenticity to tales of adventure. These creative liberties are not errors, they are the natural process of storytelling. Culture absorbs intriguing fragments of the past and reworks them to fit contemporary narratives about heroism, exploration, and the allure of lost knowledge. The Sunstone, in this context, stops being a specific answer to a specific problem of cloudy seas. It becomes a versatile symbol. It represents the idea that our ancestors possessed secrets we have forgotten, that the past holds elegant solutions waiting to be rediscovered, not in a lab but on a quest. This widespread popularity is a double-edged sword. On one hand, it is a tremendous victory for awareness. More people know the word Sunstone today than at any point in perhaps the last 500 years. Documentaries explore it, podcasts debate it, and articles feature it, all driving public interest in Viking history and maritime archaeology. This cultural buzz can even fuel real scientific inquiry, attracting funding and fresh minds to the field. Yet, on the other hand, the simplified, mythologized version can overshadow the nuanced, evidence-based reality. The public imagination often settles on the most dramatic version of a story, the crystal as a magical GPS. This can make the true historical achievement seem almost disappointing by comparison. The real story, however, is more profound. It is not about a magic rock, but about human adaptability. It is about a culture studying light scattering through a mineral with such intense focus that they could pull direction from an overcast sky. The glamour of magic can sometimes blind us to the deeper wonder of attentive, practiced skill. What we are witnessing, then, is the latest chapter in a very old process. The image of the Viking navigator has never been static. It evolves with each generation, reflecting our own values and questions. In the 19th century, the Romantic era painted them as noble, tragic barbarians. In the 20th, they were often framed as ruthless adventurers or ingenious engineers. Today, in an age fascinated by ecology and indigenous knowledge, we are drawn to their role as masterful readers of the natural world. The Sunstone fits perfectly into this modern framing. It represents a kind of green technology, a sustainable tool that worked in harmony with environmental patterns rather than dominating them. Our culture seizes upon this aspect, amplifying it, simplifying it, and blending it with our love for fantasy. In doing so, we ensure the Viking pathfinder remains a relevant, compelling figure. We are not just learning about their history, we are in a continuous dialogue with it, using fragments like the Sunstone to tell ourselves stories about human ingenuity, our relationship with nature, and the enduring appeal of mysteries wrapped in the fog of time. The crystal's light, once used to find a physical shore, now helps us navigate our own cultural imagination, illuminating what we choose to value from the depths of the past. The Sunstone's light reveals more than a hidden sun, it illuminates a hidden age. This single object forces a profound shift in perspective, challenging the very label we have long given to the centuries that followed the fall of Rome. The term Dark Ages implies a blanket of ignorance, a time when the light of classical learning was extinguished and human progress paused. Yet here, from within that supposed darkness, comes a tool of subtle optical science. The Vikings did not stumble upon this method by accident. They developed it through rigorous, repeated observation. Their innovation implies a working knowledge of light's behavior that was not recorded in a philosophical treatise, but encoded in practice. They observed that light through a cloudy sky had a consistent, directional quality that a specific crystal could reveal. This is not superstition, it is proto-science, a form of technology born from direct engagement with the natural world. It suggests that what we call the medieval period was not an empty void between classical and Renaissance brilliance, but a different kind of intellectual ecosystem, one where advanced knowledge often lived in the hands of craftspeople, sailors, and farmers, not in the libraries of scholars. This practical genius was widespread. Consider the cathedral builders of the same era, who mastered structural engineering and complex geometry to raise stone vaults toward the heavens. Or the agricultural revolution that introduced the heavy plow and three-field crop rotation, innovations that quietly transformed European society. These were not the work of a populace stumbling in the dark. They were the solutions of people intently studying their environment and solving real, immediate problems with remarkable creativity. The Sunstone belongs to this category of lived science. It asks us a reflective question. How much other sophisticated practical knowledge from this era has been completely lost to us simply because it was never written down in a formal text? How many other tools, techniques, and environmental understandings were transmitted solely through apprenticeship and oral tradition, only to vanish when that chain was broken? The Viking pathfinder did not need to write a paper on polarization to use it effectively. His laboratory was the deck of his ship, his data set was a lifetime of gray skies, and his legacy was a successful crossing. By recognizing this, we reframe the Viking Age, and indeed much of the medieval world, not as a prelude to real science, but as a vibrant, adaptive intellectual tradition in its own right. It was a tradition measured not in grand theories, but in reliable results, in ships that reached distant shores, in crops that fed growing populations, and in structures that defied gravity. This view grants a new respect for our ancestors, not as primitive figures waiting for enlightenment, but as ingenious problem solvers whose technological legacy is woven into the very fabric of how we learn to navigate our world. Their light was different, but it was never out. The true story of the Sunstone is not owned by any one field of study. It is a tapestry woven from threads pulled by historians, physicists, and archaeologists, each working in their own corner of the world until the pattern finally emerged. This is a modern detective story, and its breakthrough came not from a lone genius, but from a chorus of different kinds of expertise learning to listen to each other. It began with a physicist, perhaps, reading an English translation of an Icelandic saga during a quiet moment. Where a literary scholar might see metaphor, the physicist's mind immediately recognized a physical phenomenon: polarization. That spark of recognition, that leap from a narrative to a testable optical principle, was the first crucial connection. It transformed a myth into a hypothesis. Meanwhile, in a museum storage room or at a dig site, an archaeologist was carefully brushing sediment from a strange, translucent object recovered from a shipwreck. To the untrained eye, it was a pretty rock, but to the archaeologist trained in material analysis, its composition and worked edges told a story. Mineralogical testing could confirm it was ICELAND SPAR, and its context among navigation tools suggested a purpose far beyond ornament. This artifact provided the physical anchor, the tangible thing that demanded an explanation. Elsewhere, a historian was poring over climate records, not from satellites but from ice cores and tree rings. They were building a data-driven portrait of the North Atlantic's past temperament, proving that the voyages described in the sagas coincided with a specific, navigable window in Earth's history. Their work provided the environmental stage, proving the problem the Vikings faced was real and the conditions for a solution existed. Each researcher held one piece of a fractured lens. Alone, their fragments made little sense. The physicist had a mechanism but no proof it was ever used. The archaeologist had an object but no clear function. The historian had a context but no specific technology to place within it. It was only when these perspectives were deliberately aligned that the image snapped into focus. The modern toolkit for understanding the past is now wonderfully eclectic. To test the Sunstone, scientists employed lasers and light sensors in darkrooms to measure the crystal's properties with nanometer precision. Programmers wrote algorithms to simulate 10,000 cloudy day voyages, turning human skill into statistical probability. Chemists analyzed the residue on artifacts, while marine archaeologists used sonar to map wreck sites that held clues in their silent distribution. This collaborative model is the new frontier of historical inquiry. It acknowledges that our ancestors did not live in academic departments. A Viking pathfinder was at once an astronomer, a meteorologist, a zoologist, and a physicist, all synthesized into a single, vital role. To understand such a figure, we must emulate that synthesis. We must be willing to let a saga guide a lab experiment, and let a software model inform an archaeological dig. The Sunstone's rediscovery is a powerful testament to this approach. It shows that the most enduring mysteries of history are often locked boxes requiring multiple keys. No single discipline held all of them. It was the physicist's key of light, the archaeologist's key of object, and the historian's key of context turned together that finally opened the chamber and let us see the clever, crystal-clear logic inside. In seeking to understand an ancient innovation, we have been forced to innovate ourselves, building bridges between worlds of thought that were once separated by as wide a gulf as any ocean. A forgotten crystal can become a master key for unlocking young minds. The Sunstone story offers educators a rare and powerful opportunity, a bridge between the dusty pages of a history book and the vibrant, hands-on reality of a science lab. This is not just a tale about Vikings, it is a multidisciplinary case study waiting to be brought to life in any classroom. At its core, it is a lesson in physics, made tangible through a simple piece of calcite. Students can hold a crystal in their hands, just as a navigator might have, and witness the phenomenon of double refraction for themselves. They can pair it with a pair of polarized sunglasses and a flashlight, creating a simple experiment to model how light behaves when it scatters through our atmosphere. By rotating the filter over the light, they can see the hidden patterns of polarization appear and disappear, directly mirroring the process of searching a cloudy sky for the sun's bearing. This transforms an abstract principle from a textbook into a physical, memorable experience. They are not just learning about light, they are using it to solve a problem, just as their historical counterparts did. That simple act of rotation connects them across 1,000 years to a human being on a wooden ship, seeking the same invisible line in the gray. From physics, the journey expands into earth science and geography. Why was this tool so crucial in the North Atlantic? This leads to discussions about climate zones, ocean currents, and the unique challenges of polar environments. Students can map the Viking routes from Norway to Iceland, to Greenland, and onward to North America, overlaying these paths with data on prevailing winds, sea ice extent, and average cloud cover. They begin to see history not as a series of isolated events, but as a dynamic interaction between human ambition and planetary systems. The story naturally folds in lessons on mineralogy, exploring why ICELAND SPAR forms in volcanic regions and how its unique atomic structure creates its optical properties. Every scientific thread is anchored to a human story, making the learning sticky and significant. The historical narrative provides the compelling why, while the scientific exploration provides the fascinating how. This approach turns passive consumption into active investigation. A teacher might present the class with the core mystery: how did the Vikings navigate under cloudy skies? Then, rather than simply giving the answer, they guide students through the same process of discovery that modern researchers used. Students can become detectives, evaluating different types of evidence: the literary clue from the Saga, the optical principle from the lab, the artifact from the shipwreck. They learn to weigh the strengths and weaknesses of each source, to build an argument based on converging lines of proof. This mirrors the real work of historians and scientists, teaching critical thinking and the nature of evidence itself. It shows that knowledge is not a list of settled facts, but a living, debated, and reconstructed understanding. The Sunstone transforms the past from a static portrait into a dynamic workshop. It demonstrates that our ancestors were not primitive, but profoundly observant and innovative, using the materials and principles of their world to achieve extraordinary things. For a student, this is an empowering realization. It connects them to a legacy of human problem solving. It makes science and history feel less like separate subjects and more like different lenses for examining the same incredible human journey. The classroom becomes a place where a piece of crystal is no longer just a rock, but a portal to a stormy sea, a gray sky, and the brilliant, patient mind that learned to read its hidden light. But every story we tell about the past carries a weight in the present. The brilliant image of the Viking navigator, crystal in hand, has not always been used to illuminate history. At times, it has been wielded as a torch, casting long and divisive shadows. Throughout the 19th and 20th centuries, elements of Viking history were systematically co-opted by nationalist and extremist movements seeking a symbol of supposed racial purity and inherent superiority. The narrative of a master seafaring race conquering empty lands became a dangerous myth, used to justify ideologies of exclusion and conquest. This is the shadow that falls across any discussion of their achievements, a reminder that our fascination must be tempered with ethical clarity. When we explore a tool like the Sunstone, we are not uncovering evidence of one group's destined dominance. We are witnessing a specific human culture solving a specific environmental problem with the resources and knowledge available to them. Their genius was contextual, not inherent. It was born from necessity, observation, and the slow accumulation of communal knowledge passed across generations, not from any biological destiny. This distinction is not a minor academic point. It is the ethical core of responsible storytelling. The duty of historians and of anyone sharing these stories is to carefully separate the fascinating technological achievement from the toxic ideologies that later sought to claim it. We must frame the discovery not as "look what our superior ancestors did," but as "look what human beings, when faced with this particular challenge, were able to understand and create." This shifts the celebration from a narrow claim of cultural triumph to a broader appreciation of human adaptability. It allows us to marvel at the Polynesian star compass, the Arab camel, and the Viking sunstone as parallel expressions of the same incredible human capacity to read the world and find a path. This perspective is not about diminishing the Vikings, but about properly honoring them by placing them within the full, rich tapestry of human innovation. It prevents their story from being imprisoned by modern agendas and instead sets it free as a lesson for everyone. The Sunstone's light, when handled with care, does not blind us with false notions of superiority. Instead, it illuminates a more profound and unifying truth, that ingenuity is a universal human trait, emerging wherever people look deeply at their world and dare to ask it for a way forward. Our task is to ensure that the narrative we build today celebrates that shared intelligence, fostering curiosity and connection rather than fueling old divisions. In doing so, we honor the past not by claiming it for one group, but by offering its lessons to all. Even with a compelling case, history rarely surrenders its secrets completely. The Sunstone remains a brilliant hypothesis, not a closed chapter, and its very mystery points toward thrilling new frontiers of discovery. What would it take to move this idea from the realm of high probability into the realm of undeniable fact? The answer lies in a future find, a single artifact that could act as a definitive smoking gun. Imagine archaeologists carefully excavating the buried remains of a Viking longship, perhaps preserved in the cold, anaerobic mud of a Scandinavian fjord. Among the ribs of the ship, near where the helmsman would have stood, a small, worked piece of ICELAND spar is discovered, its edges smoothed from handling, resting beside a wooden bearing dial or a set of weathered dividers. Such a find, in an undisturbed, datable context from the Viking Age itself, would silence the remaining scholarly debates overnight. It would physically connect the tool to the specific culture and moment in history we are trying to understand. Until that day comes, researchers are refining their questions and their tools, searching for subtler forms of proof. One promising avenue is microscopic analysis. Could a crystal like the Alderney stone bear invisible fingerprints of its use? Scientists are now examining such artifacts under high-powered microscopes, searching for distinctive wear patterns. The theory is that repeated, deliberate rotation in a navigator's hand, perhaps against a leather thong or within a wooden holder, might leave a unique pattern of micro-abrasions on the crystal surface. These tiny grooves, aligned in a specific rotational axis, would tell a story no Saga could, a physical record of a practiced, repetitive motion aimed at aligning with light. It would be a forensic clue etched into the stone itself, a silent witness to its own purpose. Beyond the artifact, other sciences offer indirect but powerful lines of evidence. Consider the settlers themselves. Advanced isotopic analysis of human remains from the Greenland and Vinland settlements can now trace the chemical signature of the water and food a person consumed throughout their life. By studying these signatures in bones and teeth, scientists could potentially map individual migration histories with astonishing detail. Could we one day prove that a particular individual made multiple direct crossings between Iceland and Greenland, following a path too precise to be explained by drift and chance alone? Such a biographical map would strongly suggest access to a reliable, repeatable method of open ocean navigation, corroborating the technological capability without needing to find the tool itself. The hunt for these answers is being supercharged by 21st century technology. Underwater LiDAR, or light detection and ranging, can now map the seafloor with centimeter-level precision, even in deep or murky waters, revealing shipwrecks and submerged settlements invisible to traditional sonar. Advanced material science techniques allow us to analyze the molecular structure of artifacts without damaging them, searching for residues or wear patterns at a nanometer scale. Computer modeling grows more sophisticated every year, allowing historians to simulate not just voyages, but entire centuries of trade winds, cloud cover, and ice conditions, testing the Sunstone's utility against increasingly accurate virtual pasts. This forward-looking perspective is crucial. It reminds us that the investigation into Viking navigation is not a dusty, concluded affair, but a vibrant, ongoing dialogue between the past and the future. Each new technological advance gives us a fresh set of eyes with which to examine old evidence. The story of the Sunstone, therefore, is still being written. Its next breakthrough might come from a marine archaeologist's remote-operated vehicle, a geochemist's mass spectrometer, or a graduate student's novel analysis of an overlooked Saga fragment. This open-endedness is not a flaw in the narrative, but its most exciting feature. It transforms us from passive audience members into active participants in a mystery that spans a millennium. We are left not with a full stop, but with an ellipsis, a sense of anticipation. The gray Atlantic still holds its secrets, and the crystal's true story may yet be waiting, not in a forgotten text, but in the silent deep or the subtle structure of light, ready for the next curious mind to bring it into focus. That navigator on the prow, facing the endless gray, now holds more than a crystal. He holds an entire story, one we have traced from a cryptic line in an old saga to the precise beams of a modern laser. We followed the clue from the page to the physics lab, where light through calcite revealed its hidden, polarized signature. We saw the artifact from a later shipwreck, a tangible piece of the puzzle resting among a master's tools. We watched as modern sailors aboard a replica longship turned that same crystal toward a cloudy sky and found their bearing, connecting theory to the salt spray reality of the open ocean. This was not a search for a magic rock, but for a lost way of thinking. The Viking Sunstone stands as a breathtaking fusion of deep empirical observation and applied natural science. It was technology born from absolute necessity, a dialogue with the environment so intimate it could pull a straight line from a formless void. The true genius lies in the synthesis, the crystal's physics made meaningful only by the navigator's accumulated wisdom, his memory of bird flight and wave rhythm, his patient hand learning the language of light. In our age of satellite signals and digital maps, this story whispers a powerful reminder. Our connection to the world was once built on this kind of keen, relentless observation. We learn to navigate by becoming part of the system, by reading the subtle patterns in sky and see that our instruments now interpret for us. The enduring mystery of the Sunstone, then, is no longer a gap in our knowledge. It has become a beacon, illuminating not just a clever tool, but the brilliant, adaptive mind that crafted it. It challenges us to look at the past not as a darker time, but as a different kind of light.